Okay, so hi. I'm going to talk about scale lengths of volatile features in lunar permanently shadowed regions. And this is work that I'm doing in association with Jen's resource team. So adding on to what she has presented. What's motivating this work is we want to really understand how to sample lunar volatiles. That's important for ISRU to know how the volatiles are distributed. And we know that the ice in lunar polar regions has a heterogeneous distribution on all sorts of spatial scales. We know that that heterogeneity even goes down below the spatial resolution of the instruments that have been measuring the ice in the lunar polar regions. And this is interesting because there are processes of scientific interest that are creating that heterogeneous distribution. And then that heterogeneity is going to drive the design of any mission that's going to sample volatiles in situ on the moon, including ISRU applications. So this study, what I'm trying to do is to examine that heterogeneity on a statistical basis to aid in mission planning, trade studies, and scientific interpretation. Okay, so I have built this model. It's an impact gardening model. And let's see, I don't know if this is, my cursor will show up on the Zoom, but so this block over here is showing an area of land, and the color is the altitude of the surface. So it starts a flat patch of land, and I'm gonna start generating impact craters into this area. And I, repeat this many, many, many times. This red line here down at the bottom is just showing a transect across that area. And over here, I'll show you what the altitude is along that line. So you can see things jump out in just this one little simulation. So, a couple of craters that come in, you can see that there's a little ejecta blanket here. So your altitude has gone up there as you're going across that ejecta blanket. Later on, there are a bunch more craters. You get a crater that's going, or this line cuts across a crater. So you can see you have material that's cut out, an ejecta blanket there, and so on. So you get all these craters over superimposed on each other. You get ejecta blankets and placed on top of other craters and that sort of thing. So what the model does is it does lots of runs where I generate craters using the crater production function. And I track 3 numbers for that area. I track what the actual surface is as a function of time. I track what was the minimum altitude that a surface or that ever occurred at that location. And then I also track a line that's basically 5% below any crater that gets emplaced, and call that like the devolatilization line, so that any crater that goes there may drive the volatiles out some distance below that crater. So, just by tracking those 3 numbers, I can derive all sorts of values. So one thing I can do is look from the final surface to the minimum topography. That's showing me what the thickness of or the depth to get to unexcavated material. And then if you go all the way down to the volatiles or devolatilizing, excuse me, line, that's the thickness of the process regolith. So then what I can do is I can put in an ice layer after the fact. So that ice layer can be any thickness that I want it to be, and it doesn't really matter because I know how deep I had to go to devolatilize. So any sort of ice that would have been above that devolatilized layer is gone. Anything that's below remains. So then I can derive things like, what is the depth to the ice layer? What's the thickness of the ice that remains? And how much ice has been lost? So Excuse me. So I can also, oh, thank you, Ben, derive how this would look to different observing techniques. So how much ice is still within 1 meter of the surface? That's what we would see via neutrons. Or how much ice is still left in coherent blocks on the size scale of the radar measurements. And that's how what would be visible to radar. So that's the model. And here's some of the results from the model. This is showing how over time, the thickness of the ice is decreasing with age, and showing the results from model runs where I have ice layers that were originally anywhere from 5 centimeters thick to 2 meters thick. And obviously, if you start out with more ice, you end with more ice. But when you get down to these like 5, 10, 20 centimeter original ice layers, I've blown up the plot over here so you can see them a little bit better. But after 2 billion years, you're down to less than 1 centimeter thick of ice, even if you started with 20 centimeters on average in those areas. And the error bars on these plots are the standard deviation for the set of runs that I've done. This is showing how the model's predicting what you would see with radar and with neutrons for all those different thicknesses of initial ice layers. And you can see that, and I have here dashed lines that are showing what some of our best guess of what the actual values are. And they're pretty low for both of these radar and neutron measurements. So it seems like the data is really inconsistent with there having been, a 2 meter thick ice layer at some point in the last 2 billion years, but is more consistent with there having been an ice layer that it was, somewhere around 10 centimeters thick in the last billion years or several hundred million years.
7 minutes.
Okay, thank you very much. Okay, and then so another thing that we can do is see, how many drill sites would you have to do in order to get a positive detection of water ice, assuming that you would need 1% water to get a positive detection. And so this plot over here is showing, if you have a 1 meter drill, what fraction of the area would have if you drilled there, would you get a positive detection of water ice? And you can see it's, for something that's a billion years old, we're looking at somewhere less than 30% of the sites, which is still pretty good if you started with a 2 meter thick ice layer. But if you're started with something that was a 10 centimeter thick ice layer, which is consistent with the data that we have, it's a few percent of the drill sites would have a positive detection of water ice. And then you can also do something like, do a trade. What if we wanted to design a mission that had a 2 meter drill or a 1/2 meter drill? What does that give us in terms of likelihood of hitting ice? And so this plot on the right shows the simulations there. So, this is a model that I think can be used to help planning missions and to interpret data of the heterogeneity of ice distribution. Based on these simulations, it seems like the data that we have are consistent with there being about a 10 centimeter thick ice layer somewhere in the past 2 billion years, but probably more recently than that. And that a combination of the measurements really is helpful in providing insight into the history of an ice deposit. And there are lots of little caveats to the model, and I'm happy to talk to you about the assumptions that went in there if you're interested. So thank you.
Thank you, Dana. We can maybe have like 1 or 2 questions.
If there's any questions in the room, you can come up to the microphone in the middle. Yep, go ahead. Yep, Nick.
A quick question about the caveats. So probably in the ejecta process, you're going to be moving the ice around into that layer. Are there any thoughts on maybe what that amount would be that would get preserved from the impact?
I don't have, I mean, I have not included that in, but actually, there's a way that I could just assume that there is a wetness of that ejecta layer. It's a lot harder in the model to have it be anything other than just a single number for like the wetness of the ejecta layer. But that is something that's real. If it's just a single number, it's something very easy to include.
Howdy, really cool work. I'm curious where does the 5% for the devolatilization line come from? Is that like a temperature condition?
I just made that up. So if there's a better number, let me know. But yeah, it's there is some basis to it, but it was mainly just this is something that could be included in the model pretty easily without having to really do a detailed simulation of each impact crater.
Cool. Yeah, that would be a really cool constraint to try to nail down.
Yeah.
Wes Patterson, APL. Hey, Dana.
Hey.
Good to see you. Great talk. I just wanted to maybe add one caveat to the radar conclusion you had, maybe 2 caveats. One, it depends on the spatial extent of those deposits, right? Because you get below a certain spatial extent, and the radar wouldn't see it for resolution reasons, but also the depth, right? I think what we're talking about here is things close to the surface, easily accessible. But the radar only has a penetration depth of several wavelengths. So it's possible, maybe there could be some things that we're missing because we can't see deeply.
Yeah, that's a good point. And I think I used 5 meters within the top 5 meters in my calculation. And, that may be a little bit too much, but
Optimistic,
yeah.
but
Yeah, let me know what's the right value to use there. Yeah.